All right, so guys, I had a couple of short videos for you that I hope you watched already on interference of waves and on refraction, okay, of waves, which it's kind of handy to see the animations. And I'm not able to make one single video with that with what I have here, so I have to do like each application separately. And in the first assignment I gave you on Monday, you were going to compare Newton and Huygens wave theory versus particle theory. So Newton had a particle theory of light that's called the corpuscular theory of light, and Huygens had a wave theory of light. Okay. Now each theory explains the behavior of light slightly differently. Okay, and what's happening is those theories make different predictions as to what will happen to light. Let's say when it enters glass, everyone has to agree that light bends when it enters glass because that's an observable phenomenon. But their explanation as to why it bends is actually a little bit different, okay? And it makes different testable predictions. And that's key in science, right? Like, how do you know who's right about this? Which one is right? Is Newton right? Is Huygens right? Or maybe they're both wrong. Who knows? Maybe light is something else. But the thing is if your theory makes testable predictions, in other words, if you tell me that, for example, light has to slow down when it enters glass in order to bend towards the normal, well, once the technology becomes available for us to measure the speed of light, we can test your theory and see if that's true, okay? And if it is true, then it lends support to your theory, okay? So it's a validation of your theory. If it turns out to be not the case, then it falsifies your theory and we have to change your theory, modify your theory, or maybe even throw out your theory if it's no good. All right, so what we're going to do today is we're going to look at a couple of these things, okay? We're going to start with refraction. Okay, so here I found this online, these images, and normally I would show you some of these things with demonstrations in class, but I can't really do that, so that's why I'm resorting to doing it this way. All right, so here's the deal. Newton has a theory that light is made of particles, right? So let me just tell you here that this picture goes with Newton's theory. Okay, so that one's for Newton. This one, of course, goes with Huygens' theory. Now, I actually made a more detailed video about refraction with Huygens' theory, and there's a real sort of mathematical elegance to Huygens' theory and how he explains refraction according to Huygens' principle, which I'm not sure that he came up with entirely by himself. There's Snell's law of refraction and stuff like that. But, that must have come, I think, after Huygens. So I think maybe his theory was taken up by others in the future. And so some of this may not 100% be just him. But like really, these images here show how really Huygens' theory really applies to refraction of light. Okay, and we'll talk more about those images in a moment. But for now, let's just look at it like this. Okay, here's the deal. How does Newton explain refraction? Let's deal with that first. Okay, so what happens is, let's say you have particles, and according to Newton, these particles are traveling in this direction. And it's a beam of particles, right? So here's your beam of light, which is really a beam of particles. What happens when they enter the glass? Okay, so here's a block of glass. Okay, why do they change direction is the question when they enter the glass. And according to Newton, it's all about gravity. Of course, he's kind of the expert on gravity, isn't he, right? Like that's his whole thing. So he uses his knowledge of gravity and says, look, when the light particles are moving through air, the air molecules that are, he doesn't really know about molecules, but he knew about density. Okay, so he knew that air was made of mass and it was less dense than glass. Okay, so that was common knowledge. Okay, so what happens is when the particles of light approach the glass would have a higher gravitational, you know what, I need to change the thickness of my pen just a moment. Okay, has a higher gravitational pull, okay, on the particles of light. And according to Newton, the particles of light, for him, everything would have gravity. So particles of light had to be made of something, right? So for him, they were made, like for Newton's theory, these particles of light were made, they had a mass, like they were a very small mass, a very like, you know, he thought it must be incredibly small because like if you get hit by a beam of light, no one feels the momentum of those particles or anything like that. So he figured the mass was incredibly tiny, but not zero, okay? So, in other words, light would be affected by gravity, okay? And so this glass block has these really large, let's say, molecules in them. That would pull, okay, you'd have this gravitational pull, okay, pull toward the glass. Whoops, that's not toward. And now, once they enter the glass, they move faster because of that gravitational pull. In other words, there's acceleration here. And then once they enter the glass, okay, they're moving faster, but they don't continue to accelerate because once they're under the glass, they're surrounded by glass particles now, and then the gravitational pull sort of balances out in all directions because you're surrounded by all these molecules of glass. And so what happens is now it travels at a constant speed in the glass, but faster. That's the key. Faster in the glass. Okay. Now to understand this analogy a little better, there's this analogy of using a ramp. Now I would have shown you this in class. Let's say you have this marble that is, let's say this is air here, and let's say this is glass down here, okay? And what Newton is really saying is here is a marble rolling, a particle of light, okay, rolling towards the glass, and then when it gets close enough to the glass, there's this gravitational pull. So to simulate this, we use this ramp, okay? And what happens is the marble accelerates down the ramp, and it really does bend, okay? Here, like this is the angle of refraction, let's call it. And this is the angle of incidence. And a marble really would bend towards the normal, okay? This line here is called the normal line, okay? So it really does bend towards the normal when it rolls down the ramp, right? And it does that because it speeds up as it accelerates down the ramp. So this is Newton's explanation, right, of what light does when it enters glass, okay? Now, here's the deal. What's happening, the key is that the marble is moving faster here and slower here, okay? And I'm gonna slower there, faster there, okay? So if I was to summarize this for you, okay, I'm gonna write it over here. So for Newton, okay, I'll zoom in a little. For Newton, he said the gravity in more dense media, okay, accelerates the particles of light and makes them bend toward the normal. Okay, so it accelerates the particles of light and makes them bend towards the normal. And therefore, the speed of light in air would have to be less than the speed in glass. Okay? So that is a prediction. Like, they didn't have the technology to measure the speed of light 300 years ago, but we do now. And we can test that prediction. Is this true? Okay. Now, spoiler alert, we know that it's not true. Like, in other words, Newton was proven wrong. And in fact, he was proven wrong over 100 years ago, okay? So they were able to measure the speed of light about 100 years ago when these two guys named Michelson and Morley invented a device called an interferometer, okay? And once we could measure the speed of light in various media, we found that Newton was definitely wrong, okay? So, but it's important that theories that you have make predictions like this so that we can prove you right or wrong. So this is a prediction, so we call this a testable prediction. Okay? All right, so that's Newton, and that's how he explains refraction. So we see these images here. That's how he explains it, okay? So now, what about Huygens? Well, for Huygens, I showed you, if you watch the video that I've already posted about this, Huygens explains refraction very differently, okay? So what happens is waves do bend, and they bend when they change speed, okay? So here you see this image, and I'm going to try to highlight these waves for you. This wave here, that beam, is the incident ray of light, okay? And this, I'm going to label it, here, let me label it in black. That's the incident ray. This is the reflected ray, this blue one. And this is the refracted ray. Now remember, both Newton and Huygens agree this is the black line here is the normal. This is the angle of incidence, and this is the angle of refraction. Okay? They both agree that the light bends towards the normal, but one, Newton says, because it speeds up. But that's not the case for Huygens, okay? Now, if you watch the video, this red wavefront right here, this red wavefront that I'm just sort of coloring in red again, that red wavefront is slower, okay, than the black one was in the incident media, okay? And the blue reflected one, it's slower, so it trails behind. And because it trails behind, it changes direction, okay? So anyway, this red wave has bent towards the normal for exactly the opposite reason that Newton is predicting, okay? Now, if you look at this, I just want to show you this as well. These waves, this here would be, here, you know what, let me use a different color. Go to black. That is the wavelength, okay, of the wave, okay, in the incident media. It's the distance between two crests. Well, here in the refracted media, and I'll use this rainbow color, this distance here is the new wavelength. And what's happening is, according to Huygens, not only are they changing direction, they're also getting closer together, these wavefronts, okay? And again, he makes two testable predictions, okay? He predicts, number one, that light has a wavelength, okay? And wavelengths can be measured, whereas a beam of particles has no wavelength, right? So if you look at this, there is no wavelength here in a stream of particles, okay? There's no, don't think of these as waves, they're not waves at all. And according to this picture here, these are not waves, there is no wavelength. I mean, we're literally firing marbles at you, okay? So like, I mean, there is no wavelength there. If I shoot the super soaker at you, that stream of particles, there's no wavelength to it. It's just, I'm hitting you with a beam of water molecules, right? Okay, whereas here, there's a wavelength between these waves. This is the wavelength, right? So Newton would predict no wavelength at all, no measurable wavelength. But Huygens, it's a very different prediction, right? So he would predict that you would definitely get a wavelength, okay, so that one day might be measurable. Okay, and the other thing he predicts is that the waves would have to slow down in order to bend towards the normal, because that's what waves do when they slow down, is they bend towards the normal. So this is important. It's sort of a key distinguishing feature between these two theories, is that they make opposite predictions about what happens, okay, in refraction. So this is Huygens' explanation, okay. Waves bend towards the normal. when they slow down. Okay? And therefore, the speed of light in air would have to be greater, okay, than the speed in glass. And this is the opposite, and I'm going to write it in capital letters, opposite prediction to Newton's theory. Okay, so we have these two competing theories, and they make opposite predictions about what happens to light when it enters glass. Okay, Newton predicts that they speed up. Huygens predicts that they slow down. Okay, who's right? Well, unfortunately, they both went to their grave without knowing who's right about this. Okay. And it only came about 200 years later that we had the technology to actually measure the speed of light. Okay, speed of light is a very difficult thing to measure. Okay, and yeah, okay, so that is the refraction. Okay, now I wanted to talk a little bit more about Huygens' theory. Okay, I already told you the spoiler alert. I already told you that 200 years later, Huygens was proven right. But here's the deal. Okay, if Huygens is right, then light waves should be showing something else as well. So let's talk about interference. Now, this was not on the list of things I wanted you to look at for the two theories. But here's the thing. This is exclusive to waves. So it's another prediction. If Huygens is right, then light should show interference, right? Let's say two beams of light cross. They should show evidence of interference, okay? Yeah, and for Newton, they should not show it, because if you show interference happens, case closed, it's a wave, because only waves do that. Beams of particles, they collide, they don't interfere. You know, when two streams of water cross, you get this big splash and everything, but you don't get interference patterns. I mean, that doesn't happen, okay? So, but when water waves cross, just waves, they show interference. And so this is a key difference between these two theories. And here, I'll call this, just let me show you here. This is before. And if you watch my other video, I showed you an animation of this. This is during. So here's where the interference is happening when the two waves meet and they overlap. And then this is after. So what happens when waves interfere? Well, let's call this the tall wave A. I'll label it up here, A and B. A is moving this way, B is moving that way, okay? Now when they meet, you get A plus B. In other words, their two amplitudes add up, okay? And we get a standing wave that it's a supercrest, okay? So the standing wave supercrest does not appear to move laterally in either direction. Okay, that's why we call it a standing wave. But then after that, we still have B, and B is still moving this way. And we have A, and A is moving that way. And here's the deal. We've got, this is interference, okay? When the two waves meet is where the interference takes place, and we get, in this case, constructive interference with the two crests, okay? So anyway, that's it. Okay, that's the principle of superposition. Now, according to Huygens, light should produce interference. Okay. Newton, no interference. And here's the deal. they did not, well, look, there's examples of interference of light all around us actually, okay? But they didn't recognize it at the time. So let me give you some examples. If you ever looked at a soap bubble, the color of the soap is transparent, okay? But have you ever noticed swirls of colors, sort of this iridescent colors, usually secondary light colors like cyan, magenta, yellow? Next time you blow a soap bubble, just look at it. I know you know what I'm talking about, okay? You'll see the same sort of colors that you would produce, let's say you got gasoline that's on the road in a parking lot and it rains and the road is wet and you see this like sort of iridescent colors in the gasoline. That is called thin film interference. It's a phenomenon of light, okay? They probably would have seen that back then, okay? In fact, butterfly wings have thin film interference, but they didn't realize it, okay? They didn't realize that that was interference they were looking at. There's other types of interference that you can see, for example, it's kind of ironic, but Newton made this apparatus called Newton ring apparatus, where you could see interference of light waves there, but they didn't recognize it at the time. So let's just fast forward, okay, to the mid 1800s. And two things happened. One, they were able to show, they found, I should say, that light travels slower in more dense media. So score 1 for Huygens, right? 2, light produces interference. They figured it out, how to do a repeatable experiment where they could see the interference of light waves. And in fact, they used it to measure the wavelength. 3, they can measure the wavelength of light waves. Okay. Now, one more thing, okay, that was considered a real weakness of Huygens' theory, and this is why Newton's theory was preferred, actually. How do light waves make it through a vacuum? If light is a wave, what is the medium in space where there's a vacuum? All other waves could not propagate through outer space, sound waves, water waves, so on. You have to have a medium of some kind. But there is no medium in outer space, but light makes it through space, no problem, right? In fact, that's how it gets from the sun to the earth. So how do you explain it? Well, the ether was proven to not exist in the mid-1800s also. But what they found was they discovered electric and magnetic fields. Okay? And what happens is light is a disturbance. So what's waving? Not ether, turns out, but electric fields. That's what's waving. Okay, and these fields exist in outer space. Okay, and they are made of energy, not of matter, and that's why like it's still a vacuum. Okay, and so here's the deal: all of this came together in the mid-1800s. They figured everything out, and in fact, this electromagnetic wave theory, okay, which Huygens didn't know what kind of wave it was. So now they figured out what kind of wave it was, this electromagnetic disturbance, okay? So it's a wave that, sort of picture the Van de Graaff machine with this electric field around it because like it's got a charge, right? Well, when there's a change in that field, a fluctuation will propagate out through the field. Like let's say we turn off the Van de Graaff machine or discharges, and that the field will collapse, but it collapses at the speed of light. okay? So this disturbance will travel out from along those field lines, okay? And that's what light is. In fact, if we were to turn on a radio in the room and someone was using the Van de Graaff machine, and then you let it discharge, you would hear a pop in the speaker of the radio because it's producing radio waves, which are forms of light, as it charges and discharges, okay? So anyway, it all came together in the mid-1800s to support Huygens, right? We figured out what kind of wave it was, how it gets through space. These are all the weaknesses of Huygens' theory that were true in his time, okay? They showed that it produces interference, they showed that it slows down, and wow, they got it all figured out. So therefore, okay, Huygens was proven correct. Now, his theory required modification, so forget the ether, okay, so that was not correct. But like that's how science works, right? So we modify the theory over time, making it better and better and better, okay, according to new information that comes along, okay? And if any information comes along that falsifies your theory, well, we'll throw it out, right? And that's what happened to Newton, okay? And Newton, okay, Newton's theory was falsified, okay? So that's what happened in the mid-1800s. Really cool. So now we're going to look at what happens. That's the next stages. This video is getting long enough for now, okay, for this morning. But the next stages and what we're doing is we're going to look at now what the wave theory of light is, how that all works, you know, how interference works with light, and different experiments that we could do that we would have done in class to measure the wavelength of light, let's say. We could have done it. I'm going to have to show it to you, but I can't. Unfortunately, we can't do it together. It's kind of a cool experiment with the lasers, okay? Something else Huygens did not have is a light source like a laser, which is really fixes a lot of the problems that if you're trying to use a candle or candlelight, okay? That's not a great light source to do experiments with light, okay? When you have a laser, it's amazing what you can do, okay? All right, so let's just brief introduction here, waves, okay? And I'm gonna finish it off just by talking about waves. So just a little reminder, what is a wave? Well, waves are traveling disturbances in the medium. So let's say this light wave is traveling in that direction, which is indicated by the yellow line. Here we use c for the speed of light, okay, which is v, if you like, for velocity. The green indicates a wavelength. Wavelength is the distance between two crests, or here I'll do it in rainbow down here. This would also be a wavelength, two troughs. Okay. A represents the amplitude of the wave, so I've labeled it down here. I found this picture online, so I don't have to draw the whole thing. I'm not very good at drawing these things, so that's it. Okay. Yeah, this picture here is misleading, so let's forget this for a second. Okay. Frequency, we use F for that, so we're going to use F for frequency. But anyway, so these are basically general characteristics of a wave. I would like to talk to you for the homework purposes, something called the universal wave equation. Okay, and if you did the independent unit in sound in grade 11, or if you were with me in grade 9, we would have gone over this, but the universal wave equation goes like this, that the speed of a wave must equal its wavelength divided by its period. Okay, period is the time for one wave, and wavelength is the distance between the waves. So it's just basically distance over time. Okay, that equation. This has to equal f lambda, where period is equal to 1 over f. Okay, so that's a universal wave equation, and that's going to come up later in the unit when we do some of the problems. Okay. Another thing that I'd like to mention to you, just some notes. Okay, the speed of light in air is 3.0 times 10 to the 8 meters per second. Okay, that's in air or outer space. okay? And the, okay, sorry, I got distracted there for a second. Okay, that's the speed of light in outer space. Okay, and, oh yeah, a nanometer, the thing about light waves, they have really small wavelengths. Well, visible light anyway, okay? Like you can have light waves that are kilometers long, those are radio waves, but you can't see those. So the ones that you can see all around you right now, the light that you see with your eyes, it's around 700 nanometers down to about 300 nanometers in wavelength, okay, or so. 700 being the red wavelengths, okay, down to violet, which is at around 300 nanometers, okay, in wavelength. So 1 nanometer equals 1 times 10 to the negative 9 meters. Okay, now that's going to come up as well. All right, so in the next lesson, which there's not a lot in the homework, I just want to show you where we are. Okay, I'm going to post another lesson this week because really today was just to teach you like about the history, and the history does come up in the homework and tests and stuff like that. So this is one case where that's going to come up. Okay. In this unit where we're not only going to be solving problems. All right, so here's the deal. We did this today. Okay, universal wave equation. We talked about some of the properties of light, reflection, refraction, and so on. Okay. You know, to get ahead, you might want to look at this homework on refraction, but I can do like a little lesson on refraction tomorrow in Snell's law. I haven't really given that to you yet. Okay, so I'll do that. This is long enough for today, so I'll do that tomorrow. Yeah, and 2-point source interference. We're going to be talking a lot about interference. Okay, once we finish tomorrow's lesson, the rest of the unit is all about interference and using interference to make various measurements and stuff like that. And I will show you the laser experiment, which is pretty cool. Okay. I'll have to get into the school to do it though. I left my laser at school, so yeah, I'll just do it at school. I'll record it there, and I will post the video here. Okay, so guys, for today, you should have done lesson 6 already, and then if you like, we did lesson 2, but it's just there's no homework in lesson 2. I would do lesson 3. Just there's 6 questions there, so please like maybe look at. You should have done this already, so I'm going to cross this out. Do that. Okay, it won't take very long. You might have to read the equation. I'll go over the equation tomorrow just very briefly, but it's something you did in grade 10, so it's just review refraction and Snell's law. All right, so that's it for now, guys. Have a good day. Well, I hope you have somewhere to cool off, okay, in this weather. And it's nice that we're not at school because our classroom, I'm telling you right now, would be friggin' hot. So enjoy the day, guys, and enjoy that you don't have to be in a sweltering classroom today. All right, talk to you later.